Once again, my name is Joe Wong. I'm the Chief Technology Officer for 88 Carbon Solutions. We are a domestic activated carbon producer. We have a large activated carbon production facility in south of Shreveport, Louisiana, and our pure focus, 100% of our focus, is in mercury capture for coal-fired power plants. And our corporate headquarters is in Denver. So, it's actually pretty nice that I'm following Connie and Bruce, because they've done a lot of the background discussion, and you're going to hear several of the same reoccurring comments from me as you've heard from them, so I'll pass through those quite quickly. But in today's discussion, what I want to do is talk a bit about the science and like Connie, a bit about the chemistry involved in mercury capture, because I want to ground ourselves in what is the science behind what we're trying to do. Then I'll talk about, just like Bruce talked about, was really looking across the integrated emission control system. And so, co-benefits and native capture are very important. And to put the burden on one technology to try to get you down to the levels consistently and in a full plant operation is going to be tough. So blending and co-benefits is going to be a big part of what I'm going to talk about. And then the last part is I'm going to talk a bit about activated carbon injection, ACI, and what's been happening, and also the development of different powdered activated carbons in that arena. Okay, so I'll power through the slides, but I would like to have some conversation where you might have questions, all right? Okay, so a bit of the science. Let's start off with the science. There's been a lot of literature, a lot of academic studies, a lot of DOE studies, also private company studies around what are the key things that are required for mercury capture. And so we actually at ADA Carbon Solutions took a look at that and boiled it down to three key mechanisms. And these mechanisms have been debated as far as which order do they occur and what's more predominant. But the way we look at it in developing activated carbons is to be able to take these three mechanisms and deal with them in a highly effective way. So, as Bruce and Connie discussed, the first mechanism is conversion. When you burn coal, the mercury that's emitted into the flue gas phase is typically, if not all of it, is an elemental mercury form. That elemental mercury is inert, and is relatively inert, and it is water insoluble. Essentially not water soluble. So it's very, very hard to capture on carbon, and certainly extremely hard to scrub. So the first thing one does, you have to convert the elemental mercury to an oxidized form. Another mechanism is contact. When I talk about contact, the mercury that's in the flue gas is in a very, very dilute phase, maybe 10 molecules per billion molecules of flue gas. So I was down in Texas talking to a utility, and one of the engineers popped up and said, look, that's sort of like taking 10 ping pong balls and dropping them into the Astrodome and trying to capture 9 of them, at least 9 of them, in less than a second. So it's statistically very tough, and as you can imagine, it's not an easy thing to do. But the contact is very important. The third mechanism is typically one that is forgotten and not well taken care of, and that's the capture mechanism. You've converted the mercury to an oxidized form. You've contacted it with your sorbent or whatever you're trying to remove it with, but you got to hold on to it. It can't fly back out. You have to design the sorbent so that it holds on to it, it doesn't let it go. Or you have to design your chemistry so that it doesn't reverse and go back to elemental form. So all three of these are very important. And I have a bit of a Lean Six Sigma background, and if you were 80% 80% efficient in each one of these, what do you think your capture rate is going to be? It's not a trick question. 0.8 times 0.8 times 0.8, right? 50%. And what did you hear today about capture in a wet FGD or capture or oxidation? 80% is good, 90% is good, right? If you're 90% effective on all three of these, what is it? 0.9 times 0.9 times 0.9, you're 73%. So you're not even there. So you have to shoot for perfection in all three of these mechanisms to be very effective, okay? So the second area is one that you've heard more about, is really looking at your emission train, and different utilities, different units have different emission equipment that's already existing or is operated in a certain way. So when we go in as a powdered activated carbon supplier, typically we hear, give me your best carbon. And my immediate response is, best carbon for what, right? And so that's very important that we try to understand what is happening. I think there's a gentleman in the red that asked about co-side injection. Well, in this particular case, you have a in this particular emission train, there's a SCR for oxidation. So you may have a dry sorbent injection, and you're injecting some alkali. And depending on what you want to do, are you injecting a lot of alkali to scrub the acid gases, or are you just injecting enough to reduce your SO3 level to make your carbon effective? Then there's a question around, do you put your injection of your carbon before or after your air preheater? And there's intellectual property around what you can or can't do. But in most cases, most of the EGUs put their activated carbon injection after the preheater on the co-side, where the absorption of the mercury onto the carbon is better optimized. You have a ESP or a filter fabric. We heard quite a bit about that this morning. Some utilities have scrubbers. So there's constraints also. Some utilities want to sell their fly ash. So the amount of activated carbon that's required for mercury capture may not be maybe too restrictive if you wanted to have a concrete compatible fly ash, okay? But it is very important that you understand this entire emission train that the utilities have and how they use it unit by unit. And on the front end, obviously, what kind of fuel are you burning? Connie mentioned quite a bit about certain bituminous fuel, eastern bituminous fuel, having high chloride levels, and that that helps you with your oxidation. But if it only gets you to 70% oxidation or 80% oxidation, you got to go after that other 20%. Okay, so that's how we get into a discussion with the utilities to make sure that we're maximizing all three of those mechanisms, so that the eventual mercury capture efficiency is high. Okay. So let's take another look at these three mechanisms: conversion, the oxidation, contact, and capture. You heard a lot about putting calcium bromide on coal to oxidize the mercury. That is very effective, but it only takes care of your oxidation mechanism. So most folks will say, well, I can have a high LOI. Well, the contact is very high, but the LOI is not designed to hold on to mercury. So if you have temperature upsets, or you may have leaching of the mercury, so the capture is questionable whether it's effective or unstable. As Bruce talked about, SCR catalyst, great in oxidation, and then you have to combine that with something else, right? So most people say, well, I'll go to a wet scrubber, but the capture is questionable, and he talked about re-emissions, and that's why he talked about adding wet scrubber chemical additives to complex the mercury so that it stays in the solid phase and is removed through the gypsum. So it's very important that you dissect the system and look at each one of these mechanisms and say, where is it effective? And activated carbon, if you build activated carbon in the right way, it's an engineered material, you could build and optimize all three of these mechanisms to be very effective. Okay? So let's talk a bit about native capture. We talked about the mechanisms, we talked about the integrated approach across all the air control equipment. So we've done over 85 full-scale trials over the past 2.5 years at different utilities using different fuel blends. And obviously, as Bruce mentioned, when we go in, we always want to get a baseline. You know, how much mercury are you removing with your existing equipment, existing average fuel type and such. And I would say on average, the native capture, or the capture without any additional control technology, is typically around 40%. You're getting 40% of your mercury out, okay? But what we've found is that you can't depend on that because it varies. And on top of that, your native control typically is passive because you're using equipment that's designed to do something else. The SCR catalyst is designed to reduce your NOx. Your scrubber is designed to remove your acid gases, your SO2, HCl. And so there's not really a knob that you can turn if your mercury goes up or down based on your fuel changes in your mercury in your fuel. So we call it basically your native control, native capture is typically a passive control technology. You get what you get, and you can't really change it. If your SCR catalyst degrades over time, there's no other button. Maybe you can increase the ammonia, but it's not for mercury capture. You're adjusting it for NOx capture. High degree of control is the exception. So you have to, in most cases, have to use some co-benefit or alternative technology to complement your native control. You may sub-optimize, as I mentioned, the original design of your equipment. The wet scrubber is supposed to remove SO2, your acid gases. So you're focusing on trying to remove mercury at the same time, and in many cases, you're going to be sub-optimized. Changes in processing conditions, you don't get an immediate response from your native capture equipment. And ash LOI is not a stable capture medium. Okay? It doesn't have the pores required to hold on to that mercury. We've seen inconsistent performance when you just depend on LOI on the carbon. So this is the discussion around native capture. So you have to complement and supplement your native capture. So the area that I'm in is, and our company is in activated carbon injection. So let me give you a genesis of the development of activated carbons for mercury capture. It really started back in the 1990s, where there was a lot of pilot work looking at evaluating the co-benefits of native equipment plus activated carbon. The activated carbon side, however, was really in its infancy for mercury capture. So most of the carbons that came out of the 1990s were carbons that came out of the water treatment area. And these carbons were for large molecules, liquid phase molecules like color bodies. And the contact time was very long, and it was a liquid phase. The temperatures were ambient type temperatures. And so these carbons were water-based carbons that were adapted to a very demanding gas phase, high temperature, kinetically limited environment, and they performed to some extent, but they weren't optimized. So you saw injection rates in the order of 10, 15, or 20 pounds per million ACF to get adequate mercury capture. Since then, or in the early 2000s, people started putting some more emphasis on looking at the mechanisms and improving the carbon. And the biggest technology advancement was the use of halogenated treatments on activated carbon. And so that really took care of the oxidation. As you remembered, on the elemental mercury, it's not easily absorbable onto carbon. So when the powdered activated carbon providers started halogenating their carbons, it really helped reduce the amount of carbon required for good mercury capture. And then there was issues around ash and just ash disposal and identification, and obviously we've heard quite a bit about measurement issues. Then today, if you look at today, powdered activated carbon providers are very focused on the science and developing advanced products, and even taking it into the future. We're really looking at specific air quality control equipment requirements. You know, do I have a high SO3 environment? Do I have a high temperature environment? Do I need concrete compatibility? You know, do I need sorbent compatibility if I'm injecting trona on the front end for acid gas removal? So there's been a lot of customization, a lot of collaboration to really make the carbon solution be very, very specific and customized to a particular need. But you know, what we see in this evolution is that activated carbon is the best available control technology, and it's improving. It's improving every day. Okay, I'm going to shift gears and talk a bit about activated carbons. So when we look at activated carbons, there's really three features of the carbon that we tune. And believe me, there's a lot of different things that you can do to an activated carbon. It's an engineered material. So we can change the surface of the carbon. And when we say the surface, it's the orange colored outline in this particular particle, okay? And so it not only includes the external surface, but also the internal surface area that covers the pores or the holes that are in the carbon. And I'm going to talk a little bit more about this, meaning that these surfaces you can do a lot of different things to. You can put chemical reagents, you can put catalysts, you can change the chemical functionality. And these are the things that powdered activated carbon producers do now. They modify the surface, and I'll give you some examples a little later. The pores, these are the holes that are varying size that help you contact the mercury, and they help you transport the mercury molecules into the tighter pores, the smaller pores, where they're captured. It was very interesting. I was with one of our salespeople at a customer account, and a question was raised by the customer. And the customer says, well, you know, what's going on here? You have more fixed carbon than another competitor. You have more fixed carbon. I said, and it's very counterintuitive. Actually, if you have a high level of fixed carbon per gram of carbon, that basically means you have less activity, because what we're really selling are the holes. So we're selling air. Right? So counterintuitive to a salesperson, right? But that's what we're doing. We're selling the cavities, and we're selling the big hose for transport and the small hose, right? The last feature is the particles. So the particles transport the surface area and the pores into your emission system where you need it, when you need it, and it comes out through your particulate matter equipment, and then you can collect it, and the mercury is captured and sequestered in the pores of the carbon. Right? So we modify, or powder activated carbon producers modify these three parameters, these three features, both individually and collectively, to get to the properties that you want. So let me give you an example of one. So who here thinks that surface area is important? okay? Everyone should. It is. But it's misleading if you think that the higher the surface area, the better, right? Here's an example. We've done some experiments in our activated carbon plant where we're taking lignite coal and we're activating the coal, just like a utility is burning the coal, but we're doing a controlled burn. We're not burning it all the way. And we have an activated carbon injection system in our flue gas. And we're able to test different carbons. And what I've done here is that here's a series of different carbons that were tested. And we plotted a mercury number, which is essentially the higher the number, the more mercury capture per gram of carbon, okay? But we plotted the total surface area of the carbon from 350 up to 600. And look here, we get some really good capture across the whole range. So yes, surface area is important, but it's not the only property that's important. And here's why. Here's a cartoon that depicts the surface of a carbon. So when we look at the chemistry of the surface, we have identified 4 things that are very, very important. The first is that you can bring reactants on the surface of your carbon to be in contact with the mercury that's in the flue gas. Okay? So in our case, we use a halogen. We use a bromine salt, and we put it on the surface of our carbon particle. So this particle is dispersed in the flue gas, and the mercury comes in contact with the halogen. So you guys heard everything about what's important about using halogens to oxidize. So that's number 1. 2, someone here has talked about oxidation catalyst, the SCR catalyst. Well, there's minerals in activated carbons that some of them actually perform as an oxidation catalyst. Evan Granite of NETL did some studies with platinum and gold, and believe me, we don't put platinum or gold on our carbons, it's too expensive. But you can have a oxidation rate that's 100,000 times faster, you know, on a heterogeneous surface of a solid versus a homogeneous oxidation in the gas phase alone. So the catalyst can speed up the oxidation reaction. The other thing that we know that we've done some studies on is moisture level. We've actually bone dried our carbons, and we've gotten very, very low mercury capture, even if we oxidize the mercury. So what does that tell you? Well, that's very interesting, because when you oxidize mercury, what happens? It becomes water soluble. So moisture on the surface of the carbon actually plays a role with diffusion and solubilization to help the mercury transport into the tighter pore structure of the carbon. So that's another important factor. And the 4th factor is very specific to the flue gas. We look at flue gas, and we look at the flue gas chemistry, and we, in some cases, we adjust the chemistry, the functional groups, on our carbons to match up with the flue gas chemistry. So for example, if you have a high sulfur fuel, you're going to have high SO3, sulfur trioxide levels. There are things that you can do chemically to prevent the sulfur trioxide from interfering with the absorption of the oxidized mercury on the carbon. Okay, so the reason why the surface area isn't the only property is because of these 4 other factors that you need to consider. All right, so we tune this also. When you do that, when you adjust the surface area, you adjust the surface functionalities, the pore size, and the particle shape morphology, you're able to do some very remarkable things with your carbon. This is a full-scale trial that we did with a PRB coal, 200 megawatts. The emission train was boiler economizer, activated carbon on the hot side, injection, ESP stack, very simple system. Mercury SIMs were used. So when we talked about generation 1 type carbons, we tested a generation 1 and a generation 2 type carbon in this particular test. You saw that the typical plot that you see in assessing performance is the mercury emission rate at the stack in pounds per trillion BTUs, and the pounds of carbon injected per million atmocubic feet of gas treated. Okay, so generation 1 carbons, this is a fingerprint of generation 1 carbons. You start injecting, your initial concentration of mercury goes down, it's a steady capture, and in this particular power plant we got compliance at 3 pounds per million atmocubic feet. And actually, to operate in a margin, you probably want to operate down here at 1 pound per trillion BTUs. So you're at 3.5 pounds per million atmocubic feet injection rate. Well, the new carbons that are coming out that are much, much more efficient are quite reactive, meaning that you add a little bit of carbon and you get a significant, very reactive, fast capture. And then the capture continues down to very low residuals. So you see from a generation 1 to a generation 2 type carbon, you're seeing close to 30–50% reduction in the amount of carbon required today versus back in the early 2000s and the late 1990s. This is a real fingerprint of a very highly efficient, effective carbon for ESP applications. The other thing that you'll notice here on a generation 1 carbon I didn't mention earlier was that this capture slope is very shallow. Right? It takes a lot of carbon to move the capture a very small amount. So some carbons come down here and just flatten off and come to an asymptote. So the more carbon you add, it doesn't mean that you're going to get more capture. So there's a limitation here. Okay? But the new carbons actually come all the way down and are very, very effective. So you should be asking for a generation 2 and generation 3. I'm sorry.
John,
Yes.
when you say generation 2, is that mostly making adjustments to the surface area? You were talking about the previous slide, or is that additional adjustments?
Yeah, it's typically, you know, the pore, you modify your surface particles and pores, right? So you all 3 of those, right? Okay. So you're trying to oxidize, contact, and capture, and if you can improve those through the surface modifications, particle modifications, that's what you're trying to do. Here's an EPRI study that was done at Coal Creek. And once again, the yellow is a second generation carbon. This is for a lignite coal, and you come straight down, very steep capture and to low residuals. So this is just an example, another example of the fingerprint that you should see on a generation 2 type carbon. Very steep capture, low residuals at a very low injection rate. So, as I mentioned, the generation 1, there's been a lot of advances in activated carbons. And today, the industry has moved beyond the generation 1 adaptation of water-based carbons. Now we're talking about generation 2 that are quite innovative carbons that have very steep mercury capture and high efficiency for mercury capture. And then a lot of the pack suppliers like ourselves are moving towards collaborative development that are customizing carbon specifically for units, different units within a emission train. And these could be very, very specific requirements that the utilities are looking for. It could be concrete compatible. It could be, I'm injecting trona as a DSI, and I need a carbon that's compatible with that trona because trona requires that you inject more carbon. Or it could be that my co-side ESP is not really that efficient, and instead of operating at 280 degrees Fahrenheit, I'm operating at 390. I need a carbon that allows me to operate at those temperatures. And there's a myriad of other cases that we face that are opportunities for carbon producers to really fine-tune their product and improve efficiency. Any questions up to here? Okay, let me keep going then. Let's talk a bit about sorbent injection, the requirements. It requires that for most people to have a silo and equipment for controlled injection of the sorbent into the duct prior to the ESP or prior to the filter fabric or even in the scrubber. And the sorbent has, as I mentioned, has to be designed to really be effective in the contact, convert, and capture mechanisms. And they have to be able to be removed, effectively removed in the ESP, the baghouse of the scrubber, so that you can get the mercury out of your system. Okay? And there's all kinds of equipment. There's all kinds of vendors that provide this equipment, and all the pack suppliers work very closely with these equipment vendors to help the utilities design the right application for their use. Okay, and there's a myriad of, well, a handful, not a myriad, but a handful of powdered activated carbon suppliers, and they're all in the ICAC Buyer's Guide. Okay. All right, I'm going to leave you with a perspective. It's our perspective from ADA Carbon Solutions standpoint. We've run over 85 full-scale utility trials over the last 2.5 years. And we've collected this information and created what we call guiding principles. So I'll just go over some of these. It sounds like a broken record, but you've got to be very effective in this conversion, contact, and capture. Each piece of equipment in your emission tray needs to contribute to this. And in many cases, 90% efficiency on each one of those is not enough. Okay. The second guiding principle is adopt engineering controls, active controls. Engineers, operators, and plants like levers to turn up and down, to adjust. So you got to have a technology that is active. If you go down in load at night, you don't need as much mercury capture. Can you turn that down? If you have a hot day or you're in the middle of August and you're churning out, you have high load or you're exceeding your nameplate capacity of your boiler, you're going to have more mercury come out. Is there a technology that you could turn up? That's what you need. You need active control. Take advantage of your co-benefit capture from your SCR, from your scrubber, from any other piece of equipment that can contribute to your capture. But don't sub-optimize your existing equipment that was designed to do something else to capture mercury in addition. So make there's this issue around balance of plant. So yeah, you can put a lot of bromine on the front end, but is your equipment designed to withstand the potential corrosion, right? Or is your equipment designed to take care of the extra bromine in your wet scrubber blowdown liquid that's going to your waste treatment that goes out to the river? So always take into account the original design of your equipment, what it was for, and also avoid balance of plant issues, which is what I have here. And then take advantage of the advanced carbons that are out there in the marketplace. They're really good. Different suppliers have different specialities, and they can perform. And the other thing is that each unit of the 85 tests that we've done, we've learned something new on every single test. Every test, bar none. So testing is very important. That's all I have. Questions? Yes, sir.
Try to capture all the activated carbon so it doesn't add anything to the
PM.
Okay.
Right.
So it's not a concern for greenhouse gases.
That is correct. When you're putting more burden on your PM equipment, by injecting carbon, I mean, in some cases, the carbon loading is really not that high. In other cases, it could be very high, and that's the reason why the benefits of some of these advanced carbons is that you can reduce your injection rate significantly and reduce your PM loading, or not add to it. Any other questions? Okay. Well, you have my contact, I think. And if you have any questions, just shoot me an email and I'll be more than happy to answer it. Okay? Thank you.